Recording started. Okay, so as I was describing here, that there is a easy relationship between mobile phone and landline phone. Okay, so mobile phone has call and answer, but it also has redial, add contact, and send SMS. Similarly, smartphone has all of them, and it also has send MMS. Okay, so there's an easy relationship, and this is how you basically implement it in C++ using the inheritance mechanism. Okay, so you basically say that first define the class landline phone. So these are all the attributes of landline phone, and these are the methods or member functions of the of the landline phone, and then you derive the mobile phone from landline phone using this public inheritance. Okay, and then you only define the new methods. You don't define the method, only define the new variables. You don't define the variables which are already present here. Okay, so member variables, basically data members, you don't define them. Okay, so okay, so this is how you do it, and we have seen that you can overload or override all of this depending on, so you can either re-implement which is an existing function, okay, with some modified functionality, so that is overriding, or you can also add add the overloaded version of a function. So all the functions are already present. All the functions that were present in base class are also present in the derived class. Okay, but you can also modify them like this. Okay, so and then similarly you can do it for smartphone to mobile phone. So you can derive a hierarchy something like this. Okay, um, and this can be very, very complex hierarchy. Okay, so this is just to illustrate that how just a concrete example of a small but concrete example of how you will utilize this inheritance. Okay, so are there any questions?
So what do you mean by public here?
Like we discussed last time, that this public inheritance, it's the type of the inheritance. Okay, so you are talking about this particular public, right? What does this public mean?
Yes, sir. Yes.
So this is the type of inheritance. Okay, so we have till now only discussed public inheritance. Okay, so we will discuss today other types of inheritance, but what you should know is that public inheritance is the major form of inheritance. Okay, so the it is the most used form of inheritance in coding, and it basically encodes this is a relationship. Okay, so all the semantics that we have discussed till now, right, that the existing variables of the variables, or the data members of the base class are automatically inherited into the data members of the as data members of the derived class. Okay, then the functions of the base class are also inherited as functions of derived class, and then you can do re-implementation. So you can do override, you can do you can add new functionality, and so on and so forth. This whole semantics is valid only for public inheritance. Okay, is this clear?
Yes, sir.
Okay. Okay. So,
Sir,
yes.
in the same slide, what exactly are we doing by declaring a function virtual?
We will come to that. We will come in a minute. Huh? So today itself we will come to that.
So can we also do protected inheritance so that we can only,
Can we also?
like you did public inheritance, right?
Hmm.
So what if we do protected places?
We'll come to that. We'll come to that. But public is the main thing to understand. Okay. When you are designing your own program, most of the time you will be using public inheritance. Okay. So first, get this idea clear. We will discuss the other thing now. Okay. Okay.
So the protected cannot be used, right? If we did public inheritance.
Let us go ahead with these questions. Okay. So okay. So now we discussed that. So see, the main thing you have to understand is there are two different things here going on. Okay. One is language features. Okay. Other is the semantics. That is how you will use those language features. Okay. So as a programmer, I mean, of course, you should know the language features and what the language is doing. Then only you can use the language correctly. But also, you will be able to write and, design and write good programs and, basically, and also design and write programs efficiently, quickly, is if you understand the semantics also that is offered with a particular feature. Okay. So as we discussed, with the public inheritance, the semantics is the easy relation. Okay. So, okay, this is a fun exercise. I will skip it for the time being. Okay, we'll come back, but let us go into, since there are so many questions about the other forms of inheritance, right? So what are the other forms of inheritance? So what C++ allows is, just like it allows members to be public, private, or protected. Similarly, it also allows the inheritance to be public, private, or protected. Okay. So public we have seen. So what is private inheritance? Okay. So instead of public, you just use the keyword private. Okay. Now the key thing comes that private inheritance does not mean generalization, specialization. Okay. Okay, so we will see these things again, but why is this? Okay, so let us look at this. So suppose you say that a person, okay, and then you give all the things, okay, and then you have a student, okay, and then you say public person, okay. So, yeah, so a person can eat, okay? So every student can eat, okay? This should be the natural semantics, right? And this is maintained when you do this public inheritance, okay? So I think somebody is unmuted. Can you please mute yourself? I'm getting some knowledge. It is a little bit distracting. Okay. 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 So yeah. So this is the thing. Okay. That okay. But now come to this one. Okay. So and only students can study. Okay. 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 Now here, suppose you do a private inheritance. Okay. So what happens? Okay. Okay. So let me describe this thing matrix here. Okay. So when you do, so suppose something was okay, so this is if you are doing a private, so the columns here are the type of inheritance, okay? And the rows here are the type of visibility in the base class, okay? And the entry is actually the type of visibility in the derived class, okay? So if you do a private inheritance here, okay, what happens is if something is public in the base class, okay, it becomes private in the derived class, okay? So this is the matrix, okay? Now let us go back to this particular thing. Now here in the person class, eat function was a public function, okay? But if you do a private inheritance here, okay, now this eat function becomes a private function, okay? So if you try to do eat p, it will do because p is a person. But if you try to do eat s, it will give an error, okay? So basically, you know, in terms of semantics, what is happening is that even though student is inheriting person's qualities because every student is a person, okay, but because you are doing it in a private inheritance manner, okay, the student cannot eat, okay, even though the person can eat, okay. So this is the problem. So this is why private inheritance is not, you know, following this semantics of easy, okay. Now again, protected inheritance, okay, is very so it's very rarely used, okay. So almost nobody uses. It's a language feature which exists, okay, and there is a quote by, you know, one of the experts on C++, Scott Myers, okay. So he says private inheritance means something entirely different from public inheritance, and protected inheritance is something whose meaning eludes me to this day, okay. So yeah, so even protected inheritance is a little weird, okay. um, Now this is the visibility matrix. So what happens if you do this kind of inheritance, okay? So in public inheritance, so whatever is the visibility in the base class, it remains exactly the same, okay? So public remains public, protected remains protected, and private remains private, okay? In protected inheritance, public becomes protected, okay. So basically something that was available in the for, you know, general functions, okay, or accessible in general functions in the base class now is accessible only in the member functions, okay. And it's not clear why you want to use this, okay. Other two remain the same, okay. In private, everything becomes private. So public becomes private, protected becomes private, and private becomes private. Okay, so everything becomes private. Okay, so about the okay, yeah. So again, we will come to this exercise maybe a little later. Yeah. So let us actually go to this particular thing. Okay, where you know, you are. So this basically, this slide kind of shows you the, you know, what is accessible where and so on and so forth. So, you know, there is the base class A, then B, C, and D are doing public, protected, and private inheritance of A. Okay, and this has X, Y, Z. Okay, so obviously Z is accessible outside. Okay. But from B, now you see you are doing public inheritance. So Z is accessible, and you have defined a new public W. So that is also accessible. Okay. For protected inheritance and private inheritance, again, only W is accessible. Everything else is not accessible. Okay. Now, further, if you let's say do something like you know, something like a public inheritance from B. Okay, so this is basically two-level subclass of A through private inheritance. Okay. Again, you see the object E has Z and W. Okay. So this lineage A to B to E lineage is maintained. Okay. And of course, if you do public inheritance from type C and type D, again, they have all only W. Okay, which was defined in type C and type D. So all influence of this A is kind of, you can say, not all influence basically, but at least from a public accessibility point of view, the influence of A is completely gone. So you can see that, yeah. Okay, so this is just to understand. So one semantics that private inheritance has is what is called a has a semantics. Okay, so so what is this has a semantics? So suppose you have two types. Let's say you have the type engine and the type car. Okay, now every car has a engine. Okay, so so how do you express this kind of has a relation in C++? Okay, so this is also sometimes okay. So the first is what is called a composition. So you will again you will discuss about it in UML and all. But basically, what this means is that what you do in composition. So because every car has an engine, okay. So you basically define an engine inside the car class. Okay, so this is called composition. So you are creating an instance of type engine inside a car. So every instance of car has an engine. Okay, and then suppose every engine has a start attribute. You can start the you can start the engine, and okay, so you can just define this start function inside the car, which basically calls this e.start. Okay, so when you define car C and you start C, what you are doing is actually you are starting the engine of the car. So the car has an engine, which is E, which is private. You cannot directly access the engine. Okay, but you can start it. Okay. Now, what you can do with private inheritance is that you can say that this class, you have the class engine, which is exactly same as the previous class engine. But now you can say this class car actually inherits an engine, but in a private manner. Okay. So then this all attributes of this engine, including the start function and everything, is private inside this class, but it is present. So there is a instance of engine inside this class, but everything is private. Okay. So then what you can do, you can use this kind of a using keyword. Okay, to say that you want to so you want to use the start function of the of the engine class here. So you are basically borrowing this start function of the engine class here. Okay, and then what you can do, you can basically just say car C and C.start. Okay, so this is one sort of situation where you can use a private inheritance. Okay. Okay, yeah, so basically this is the yeah, so one statement that Scott makes is that private inheritance means nothing during software design, only during software implementation. Okay, so this is a kind of a deep statement which you, when you try to do a design, you will understand basically that because none of the attributes are accessible to the derived class. So in terms of design, it doesn't make any or doesn't make much impact. Okay, private inheritance. Okay, and the second thing is private inheritance is means that it is like is implemented in terms of. Okay, it is usually inferior to composition. Okay, So there is a also, so as you saw that this has a relationship can be implemented in both ways. Okay, but this composition is actually preferred because so the only thing that you are getting here is that you don't have to re-implement it, the start here. Okay, but here also all you are doing is you're re-implementing the start, but you're calling this e.start. Okay, so that is not much of a code bloat, as one would say. So if you are fine with this much of a code bloat, then you should simply use the composition. But the advantage here is that you kind of get more fine-grained control over what APIs of the what features of the composing classes you want to expose to the person. Here you don't get that much fine-grained control. You only get if you do it with using private inheritance, then you get only at a at the level that yeah. So you get at a very high level basically. Okay. Yeah. So but it makes sense when derived class needs access to protected base class members. Okay, or needs to redefine inherited virtual functions. So we will see what this means in a in a minute. Okay, so this is about private inheritance. Okay. Yeah. So yeah. So any questions about this? I think this is fine. So this is just for completion. Okay. 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 So now we come to a interesting feature of this inheritance, which is the dynamic binding or polymorphism. Okay. Okay. So now, yeah. So before we go there, okay, we have to discuss this concept of casting on a hierarchy. Okay. So these are the things we will discuss. Okay. So just some if you remember just to remember. So casting is basically there are again we have seen two types of casting. One is implicit casting, another one is explicit casting, right? So in terms of like if we look at let's say like built-in types. Okay, so for built-in types, for example, integer and double is there. So you can simply say yeah. So let us look at it here. So you can say d is equal to I. So d is of type double. Okay, so this is an implicit cast. Okay, so integer I is implicitly converted to double. Okay. And you can also say I is equal to D. This is, but D is a quote unquote, larger or wider type. Okay, so you get a warning, but you can still do this kind of a implicit cast. You can assign a double to an integer. Okay. You can of course do a explicit cast, something like this. Okay, this will remove the warning. Okay. And then you can also do you can have a pointer type object. Okay, and then you can also yeah. So if you try to do an implicit cast from pointer to integer, C++ does not allow this. Okay, but you can do an explicit cast. Okay, so you can explicitly cast from pointer to integer. Okay, so this is allowed. Okay. Okay, so now what happens to user defined types? Okay, so suppose you have two classes, class A and class B, which are basically storing integer and double here. Okay, now if you define let's say A as an object of class A and B as an object of class B, this will give you an error. Okay, so there is no implicit cast from unrelated types. Okay, unrelated user defined types. Okay, Moreover, even if you try to do an explicit cast, still it will give an error, okay? Because there is no way of explicitly casting, explicitly doing this kind of cast, and it also goes the other way, okay? So from B to A and B to A, okay? Now, if you try to do this implicit cast with the pointers, okay, it will give you an error, okay? But if you do an explicit cast here, okay, or forced cast as it's called, then it is allowed. So forced casting of pointers between unrelated types is allowed, okay? But this is a very bad programming practice, okay? This is heavily discouraged, okay? So, yeah, so this is the problem. So suppose now you do a forced cast, okay? You have yeah, so P has I, okay? So P is a pointer to type A, okay? And Q is a pointer to type B. So P has I and Q has D, and things are properly printed. But the moment you try to, moment you do explicit cast, okay, now P is of type pointed to A. So again, P will have I, but actually your your B object is of type B, so it does not have I. So it will give some junk, okay? It will give some garbage, okay? And so that is why this is not a good idea, okay? You should never do. I mean, you should not use something like this if you can avoid. Okay. Okay. So now, what happens is when you do this inheritance, okay, then you get now you get types which are related. Okay. So in this case, this type A, I mean, so B is basically a subtype of A, okay? So if this is the case, then basically you can think that there will be two types of casts now, okay? One is, so we are looking at pointers of each objects, okay? One is called upcast, where you basically cast a pointer of the derived type, which is B in this case, to the pointer of the base type or the base class. Okay, so yeah, so if you do this, okay, this is allowed. So even implicit casting here is allowed. Okay, but the downcast, where you sort of yeah, so where you basically try to cast a pointer of the base type to the pointer of the derived type, that is that will give you an error. Okay, so if you do a yeah, so if you do this, okay, now and if you try to assign assign anything to void star, this is okay. But when you try to assign a void star to some type, this gives you an error. Okay, so basically a void star is like an untyped address. So this will not be a complaint. Okay, but the other direction will be a complaint. Okay, now why is this? So what is the logic behind this, right? So the logic behind this is that you see this is a relationship says that every object. So what was the problem here? The problem was that you were trying to access objects which, data members or any kind of members which did not exist, right? But if you do the upcast, you see every object of B has something has all the all the members of type A. Okay, so when you say PA arrow some member, okay, which is there in A, you know for sure that it is also there in B. Okay, that is why this particular upcast is allowed. Okay, but the reverse is not true. That is why the downcast is not allowed. Okay, so this is the logic behind this upcast being allowed and downcast not being allowed. Okay. Yeah, so upcasting is safe. Okay, so this example shows exactly the same thing, that you can see that see, data A will always be there in B, but the data B will not be there in A. So when you say something like yeah, so when you try to say PA is equal to ampersand B, PA arrow data A will work. Okay, but PA arrow data, so even though this is of object type, it is pointing to an object of type B, okay, which has data B, but because the pointer is of type A, this statement will give a compilation error. Okay, that data B is not a member of A. Clear? So you are safe. If you are only trying to access the common members of the object B, you can simply say that take a pointer of type object A, okay, and assign the address of the B type object to A, and then you can use it as though it's an object of type A. Okay, you can just work with the common members. Okay, so you can understand the semantics is coming out, right? So, okay. Now, yes.
Sir, B will not have private members of A, so
B will not have private members of A. No. Private members of A will be private members of B.
okay, sir. Okay.
Okay. Okay. So now you see. Yeah. So So now we get into this concept of static binding and dynamic binding. Okay. So okay. So now okay. Let me just see. Yeah. Okay. Okay. So see this. So this particular. Okay. So here. So whatever we discussed here, right? This upcasting and then accessing the member data members. Okay. This can also be applied to member functions. Okay. So for example, class B has this member function F, and it also has this virtual member function G. We will come to what this is. Okay. And now class D also has a override of the member function F, and also a override of the virtual member function G. Okay. Now what happens? So as we know, upcast is allowed. So we are creating object of type B and object of type D. Okay. And then we are also creating pointers of type 2 pointers of type B and 2 pointers of type yeah. Okay. Yeah. So we are creating 2 pointers of type B. So we'll come to the references. Okay. But we are also creating, and then we are in one case we are assigning the address of an object of type B to this pointer. In the second case, we are doing an upcasting, right? So we are actually assigning a derived class object to this particular pointer. Okay. Now, what happens in the first case? Okay, so in the first case, so even before this, you see, if you are accessing it through the original variables, okay, none of this makes any difference. Okay, only if you are accessing it through pointers or references, all this static or dynamic binding discussion makes sense. Okay, so because if you are if you have variables, okay, it will call the original the function that is available in that. So because the function f has been redefined in D, it will call the D colon f. Okay, and similarly it will call D colon G. Okay, so that is one thing. Okay. Now let us come to the pointers. So for PB, when you call f, okay, it will call B colon f at as uh, uh, so as we called, okay, and now when we call so when we call PB, sorry, let's say PD colon f, okay. Now which function will this call? Okay, now you see there is a redefinition of this function here. Okay, but the so PD is a pointer of type B, right? So it will call B colon f. Okay, because okay, so this so why is this? So we will discuss this in a minute. I don't know if we have time today. Let us see. So we can discuss this today itself. Okay, but so this is one thing. Okay. But now notice what happens with the virtual functions. Okay, so these functions G, you have just defined them to be virtual. Okay, nothing else is changing. Okay, in this case, actually, when you are calling PB colon G, as expected, it's calling B colon G. Okay, but when you are calling PD colon G, it's actually calling D colon G. Okay, so notice now what has happened actually, right? So at the compile time, the compiler sees what? Sees that this is an object of type B star. Okay, so focus on this particular thing. Okay, so this is an object of type B star which is calling this is a pointer of type B star, not object of type B star, but pointer of type B star, and it is calling a G function. Okay, so the compiler should look up the class B and call its G function. Okay, but somehow it is recognizing that even though this pointer is of type B star, okay, it is actually pointing to an object D, okay, which is of type D. Okay, and this, it is calling it here. Okay, okay, so think about it now. Okay, so actually the fact that an object of type D is getting assigned to a pointer, the address of an object of type D is getting assigned to a pointer of type B. Okay, this is not, it is not possible to determine this at compile time in general. Okay, in this particular case, that information may be available, but you can do it in very weird ways, or you can even compile. You can have different files compiled separately, or so on and so forth. So in general, this is not possible to determine at compile time. Okay, so what happens is, in this case, this virtual directive to the compiler asks the compiler to store some extra information in every object of that every object of that class. Okay, this is one thing. And a call to a virtual function tells the compiler that this call binding should happen at the run time and not at the compile time. Okay, so this is the key. So this is the difference between the static binding and the dynamic binding. So what is the difference? The difference is that in this case, okay, if it is a static function, not static function, if it is a normal member function, not a virtual function, okay, the binding happens at compile time according to the familiar rules that we have discussed till now. Okay, whatever is the type of the object, in this case the type as determined by the variable. In this case the variable is pointed to type B, so the type of the object is basically B. Okay, and it's also called the static type of the object. Okay, and accordingly the function corresponding to basically the when the binding is done for this function call, okay, you remember there was this function overload and all these things. So this entire mechanism will happen thinking that you are looking at the functions available in this B scope, okay, the scope of the B class, okay, because the type of this object is B. Okay, but that is not the case here. Okay, here this entire lookup will happen at runtime. Okay, and that too it will happen looking at the type of the object that this pointer is pointing to, not at that time. Okay, not what is the static type of that particular object or the pointer. Okay, clear? So this is what is called, this is the difference between static binding and dynamic binding. Okay. Oh, sorry. Okay, so I think, yeah. So let us see in more detail the same thing. Okay. Okay, so yeah. So in order to understand this in more detail, what you do, you basically, when you are trying to parse, a program, or when for example, the compiler is trying to parse a program, okay, it sees, for the most part, okay, it sees the static type of an object. Okay, definitely at compile time it sees the static type of an object only. Okay, so for example, in this case, the static type of P, so you can write something like this, that P is equal to new B. Okay, this you can write. Okay, where B is a subclass of, or is a derived class of A. Okay, if this is the case, static type of P is A. Okay, but the dynamic type of P is actually B. Okay, now this dynamic type is, it is not possible for the compiler to know all the time. Okay. Okay. Yeah, so this we have discussed. Basically, static binding, or it's also called early binding, is when the function invocation binds to the function definition based on the static type of the object. This is done at compile time. Okay, and normal function calls, overloaded function calls, and overloaded operators are examples of static binding. Okay, so this is something we had seen till now. Okay. Dynamic binding or late binding is that when the function invocation binds to the function definition based on the dynamic type of the object. Okay, this is done at runtime. Okay, and two examples are, one is function pointer, other one is virtual function. Okay, so these are the basically examples of late binding of function call. Okay. Okay. Now, yeah. So, yeah. So there is this thing that why should we even bother about this, static binding or dynamic binding, something like this, right? So what happens, see, so you think about this particular example, let's say, so B has a function f, and now D re-implements this f, okay? Re-implements means in a normal function, this will be overridden, okay? Because it's the same prototype, okay? So it will re-implement, and then you call the static binding comes here, and then you call the respective function, okay? Now what happens is that if you override like the some implementation of a member function from the base class, the original implementation gets masked, okay? Okay, so now yeah, okay, so here again, yeah, so this is this is simply a recap of what is override and overload, okay? So I think all of you know, so I'm just skipping over it, okay? Now one thing you can do, you can basically avoid this masking by using this kind of a using statement, okay? So suppose you had some function f, okay, and you implemented some other version of f here, okay? So this can override the original function definition, right? So what you can do, you can avoid that by basically using, bringing the original function definition here itself, okay? So this using is, you're basically saying that, look, this original member function that was defined in the base class is still valid here, okay? So that is kind of what you are saying here, and then you can use both. So if you call the usual overload resolution will take place, and if you call it with an integer, it will call b : f. Otherwise, it will call a : f. Okay, so this is what it is. Okay. Now, in case of dynamic binding, as we saw, okay, if you redefine the same function in a derived class, what it doesn't get overridden. Okay. Instead, what happens is both versions of the function remain accessible, and they are called based on the dynamic type of the object. So if the dynamic type of the object is B, then you call the function corresponding to B. If the dynamic type of the object is D, then you call the function corresponding to D. Okay. Okay. So okay. Yeah. So I just want to make a comment here, and I don't know. Yeah. So I'm almost at the end of it. So I just want to make a comment here that you see this. So where is it? So in terms of semantics, why is this useful, right? So you see what you can say. So think about now this base type as a person, okay? Or you can think of this base type, let's say, as an employee, and derived type can be either manager, or it can be something like let's say programmer, or it can be something like a team leader, or it can be something like any other employee. So let's say receptionist or something like this. Okay. Now consider the situation where you are trying to make a list of all employees of the company. Okay, so you want an array of all employees of the company. Okay. Now your objects can be of type manager, can be of type programmer, etc. Okay. But if you have an array of pointers, okay, let's say, which is of type employee star, Okay. So an array of employee pointers. Okay. You can assign all these objects to this array. Okay. So this is the, the basic use case behind this type of virtual thing. And now when you have the list of employees, let's say you want to print the employees in a different manner, or let's say you want to print the employees followed by their designation or something like that. Okay, so every employee has a name. Okay, but then managers will be called managers, and so on and so forth. Okay, so you can call a different function. Okay, you can just call, if you don't know, let's say for a person who is just an employee, doesn't have any other designation. Okay, you can just, let's say, call the employee print function, or you can call the manager print function, or you can call the programmer print function, depending on the actual type of the object. So your code becomes very, very easy and intuitive. Okay, so this is the advantage of this virtual function feature, and this virtual function is basically implemented using this late binding feature. Okay. Yeah. So yeah, I think we have discussed all this. So basically, yeah. So dynamic binding is only possible for pointer and reference data types for member functions that are declared as virtual in base. Okay, these are called virtual functions. If a member function is declared virtual, it can be overridden in a derived type. Okay. If a member function is not virtual and it is redefined in a derived class, then the later definition hides the former one. We have seen this. Okay. Any class containing a virtual member function by definition or by inheritance is called a polymorphic type. Okay, so basically, if it has a virtual member function, any class which has a virtual member function is called a polymorphic type. Okay, and a hierarchy may be polymorphic or non-polymorphic. Okay, and if it is a polymorphic hierarchy, basically what will happen is the compiler stores a special field in the object of that type. Okay, or any type of that hierarchy, where basically the type of an object, the compiler can determine the type of an object at runtime. Okay, so it has some performance implication in the sense that it bloats the size of the object a little bit. Okay, yeah, and yeah, so a non-polymorphic hierarchy has very little value. So yeah, so this virtual, as you design, you will realize that this feature is very important in actual implementation of this programs with this ISA hierarchy. Okay. Okay. So yeah. So okay. So I don't know how much time do I have. Okay. So I think I will stop here and we'll continue from here in the next class. Okay. Any questions that you have? Okay. Okay, so I see that very few people are attending. Okay, okay, so see you in the lab class. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir, could you please upload the slides in Moodle?